So one of the things that makes fluid mechanics tricky, is that most fluid flows are invisible. If you think of air, if you think of water, you can see the water, you can't see the air, and you certainly can't see the flows inside either one of them. So as a result of this, people have noticed when it is visible by, tiny bubbles being trapped or leaves floating, and scientists and engineers and inquisitive people have purposely visualized flow with any number of techniques, things like injecting dye or injecting smoke or using smoke that's already naturally there. You can also create bubbles in the flow or inject them. You can also put powders or oil on a surface and see how it flows over the surface. You can also stick little tufts of fur or hair or yarn on something and see how they flow. There's also some really advanced techniques like Schlieren, which uses some advanced optics to look at density changes, and other even more advanced techniques that aren't in this course. But regardless, the goal most of the time when you're visualizing a fluid flow is to better understand it and to determine the vector field. And as a brief aside, if you don't remember vector fields and scalar fields, we're going to be using them in this course. So go back and review your vector calculus notes, ME 201. And very often, instead of or in addition to the vector field, we're going to also look at some other types of flow visualizations, which include looking at streamlines, looking at path lines, and looking at streak lines. And we'll talk about each of these four, vector fields, visualization, and streamline, path line, and streak lines, in the next couple of slides. So how do we visualize the vector field? Well, there's a couple of computer vision techniques like PIV, particle image velocimetry, and PTV, particle tracking velocimetry. And those tiny links in the upper right will take you to some MATLAB codes that you can use to implement them. But the basic premise of it is something that you can wrap your head around and do by hand, do by eye. Because the basic premise is that you take two pictures of a flow some short time apart, and then by eye or by computer, you find the local velocity at multiple points in the flow. So this video here is showing that technique. The flow is steady from left to right, made unsteady by this flapping vane here. Each one of those dots is a patch of bubbles that was produced by electrolysis in the water flow upstream. And so the idea of visualizing a vector field is that you take two pictures. Here's one. And then the second picture that you can take and put on top of it a short time later is this second one right here. And this gives you the idea of a vector field. You can, by eye, take a look at each first particle, which you know is on the left, and each second particle, which is on the right, maybe a bit higher or a bit lower, and you can draw a line in between them. So that's what they do in this video. And then those lines are the definition of a vector field. They are a series of points, and the arrow is at the base of, or the base of the arrow starts at each one of those points. The direction and magnitude of the arrow indicates the direction and magnitude of the velocity at that point. So there is a visualization of a vector field. You know that a short time later you're going to have a different one because you're going to have a different image pair. If you've got enough particles in your flow, it becomes impossible to do by eye because there's just too many to track. But you can then get a computer to do it across all of the space in the image and then interpolate or average that out to give you an even grid. This is obviously a very uneven grid. This particular set of images also suffers from there's not any particles in the wake behind that flapping vane, so you can't see what's going on there in the wake. As an aside, this video is part of a series that was made in the 1960s. It was a group called the National Committee for Fluid Mechanics Films, mostly profs in the Boston area and other parts of the US, some from Cambridge, and at least one from UBC. And they did a fantastic job of showing fluid flows. It's a set of between 10 and 20 videos. The link there will take you to a page that has all of them in very good quality. I would recommend all of them. I'd recommend this flow visualization one especially, and we're going to use it a lot in this course. So of the three flow visualization lines, the streamline is probably the most useful. It's got a very mathematical, rigorous definition. A streamline is a line everywhere tangent to the local velocity. So it's very much an Eulerian perspective. You have to consider the entire velocity field like we've got up here in the upper right. So if you have that entire velocity field, then the streamline starts at whatever point you want to consider it starting at. And as you follow that line, everywhere along that line, the velocity is in the direction of that line. You can see that in all of those arrows. So it's very much Eulerian. That also means that there's going to be a different set of streamlines for every time period. So if this flow field changes with time, then with each different flow field, you would have a different set of streamlines. It also means that you have multiple streamlines. You can have a streamline starting here and a streamline starting there, for example. And so the mathematical formulation of this comes out from the fact that velocity is change of position with respect to time. And so that means that the distance that the fluid parcel travels over some small time is dx. And that means that dx over u is equal to dy over v. And if we're talking about a three-component flow with a z component of the velocity, it's equal to dz over w. Thinking about it with just two components for the sake of ease, if this is your velocity v made up of some component u and some component little v, then over some small time dt, that fluid parcel is going to move some dy by some dx. And if you look at those are similar triangles. They have equal angles, which means they must have equal ratios of their lengths. With that formulation, you can then write an equation to solve for the equation of the streamline. And that equation is simple integration. If you integrate dx by u equals dy by v equals dz by w from some initial point x0, y0, z0, you will get an equation for the xyz line, or this line in x, y, and z that describes the streamline. And I keep talking about x, y, and z in this course. We'll mostly deal with two-component flows where we just have to consider the x and the y, but sometimes you will see three-component flows in this course, and certainly in life, everywhere you will see them, so don't forget that fact. As another flow visualization line, consider the path line. In comparison to the streamline, it's a Lagrangian viewpoint. Pathline is literally the line that any given fluid parcel follows. So very much Lagrangian. If you want to think about how to consider a path line, picture yourself in a stream on a raft. You are at some position, and from time t equal to 0 to t1, t2, t3, you move from that initial position to whatever position you move to. Now, if other people, other rafts, other rubber duckies, other whatever, are also being considered, then they're all going to move in different directions with time as well. Mathematically, again, a very rigorous definition, and specifically, it's an initial value problem, thinking back to ME 203, thinking back to your ordinary differential equations course. Start with the same definition of velocity being change in x, y, and z position with time. If you have some initial position at some initial time, then you can run that out as an initial value problem. You can consider a small time step, update your position, and then update your velocity and keep going. You can do it analytically with something like x is equal to the time integral of u dt with x at T naught equal to X naught. And then you would have to do also Y and Z and run all of those. You can also do it numerically by considering a small delta t and updating things accordingly from there. The last of the flow visualization lines we're going to consider in this course is the streak line. So the streak line is all of the parcels that passed through a given point at some point in the past. The fancy English word for that is locus, the location of all of those points now. A lot easier to just think about it with an analogy. Think of a smokestack. You see the smokestack, the output of it is fixed in space. Over time, you see a plume coming out of it. That plume is all of the points that left that smokestack. It's the streak of all of the points that left that smokestack. Mathematically, it's the same sort of initial value problem as for a path line, except instead of some fixed T naught, you have to let T naught vary from some time in the past to the present. And you have to run each one of those from that time period to the present and find the end point of all of those path lines. There's two reasons I can think of for why you think about streak lines and why we're talking about streak lines. They are occasionally useful if you want to know where all of the pollutant that was released by incinerator when it accidentally burned something very toxic. If you want to think about where all of that went, well, you know that from time A to B is when it was burning it, and you know that it is now time C. You want to know where is the streak from A to B now. The other reason that you think about them is because they're the easiest thing to get experimentally. If you've ever seen a picture like this in a wind tunnel with those streaks going over the car or the plane or the runner or the biker or the whatever, then those are streak lines. They were released as fog upstream or smoke upstream, or you were injecting dye through a syringe into water upstream, and it's a streak. It's all of the parcels that left that smokestack or left that smoke generator or left that dye injection point, and where are they now? They can tell you some very useful things, especially in steady flow, as we'll discuss soon, but you need to remember that they are different from path lines and they are different from streamlines.